Olga, hello.
Здравствуйте. Hello.
Hello. We are ready to start our today's event. Let me say a few introductory words to the audience about the project that we are involved in. The matter is that our museum, the Tsiolkovsky State Museum of the History of Cosmonautics, has embarked on a project that is called Handshake in Space within the public diplomacy grants program of the US Embassy in Moscow. The project partners of the museum are Institute of Biomedical Problems of the Russian Academy of Sciences, Moscow Architectural Institute, and Sasakava International Center for Space Architecture, University Hьюстона, the USA. The project Handshake in Space is scheduled to mark the anniversary of the historic docking of American and Soviet spacecraft in the Earth's orbit during the Apollo-Soyuz test project, which became the symbol of the cooperation of the two superpowers in the development of science and space exploration. The project includes a set of educational, exhibition and cultural programs and events devoted to the theme of Russian-American cooperation in space. Today, we are very glad to welcome Ольга Баннова, research professor, director of the Sasakava International Center for Space Architecture, College of Engineering, University Hьюстона, the USA. Today, Olga is going to deliver a lecture, Space Architecture Enabling Living Beyond Earth Limits. Olga, just before you start speaking, we would like to introduce the audience to you that have come to your lecture. These are the staff members of the Tsiolkovsky State Museum of the History of Cosmonautics, students of Kaluga State University and their teachers, students of Kaluga branch of Bauman Moscow State University and their teachers as well, and our online audience. Now, Olga, you have the floor. You're welcome.
Thank you very much for the introduction and description of the project, and it's very exciting that we have this cooperation now. And I will go with the lecture, and then I will really appreciate if we have more about time for the discussion. So I will try to stay with the lecture maybe about 40 minutes or so. And then after that, I would prefer that you ask me questions, as many as you want, and more questions is better. Thank you very much for coming. And now I can share my screen, yes. Hold on. Okay, you can see the screen, right? The presentation.
Yes.
Okay, yeah. Okay, so this space architecture as a discipline was defined at the International Astronautical Congress in 2002 in Houston, so it's been already quite some time ago. And it's described and it was defined back then as the theory and practice of building inhabited environment in outer space. Although it did happen in 2002, but this still the human long-term presence in orbit well, so far it's only in orbit. It's mostly defined, and the designing for humans in space is mostly defined by engineering. And it still mostly remained in engineering domain up to now. So now the situation is changing a bit. So more and more space architects involved in designing for surface of the moon or for orbital facilities. In this lecture, I will talk about important aspects of the space architecture and design, and some design principles. And in general, I'll talk about, start with defining what is the space mission architecture. because we don't look at design of a habitat as just separated from the whole mission planning. So understanding how the mission, space mission is planned, what is needed, what are the goals and objectives of the mission is very important. It's like designing a house without, if it would be, without the content of the surroundings, without understanding the environment. So we don't do that, right? On Earth, we really design buildings in the fabric of urban fabric or integrated into the environment. So same thing with space. We need to understand how the mission works and how to build the elements, inhabited elements for space missions in connection with overall mission planning, in connection what people will be doing during the mission and understanding how everything is connected. So here, this example of one of the projects that students did some time ago. It's a mission to Phobos. And here is overall design process, I would say, even represented here. So first we can thinking about how everything will be launched from Earth, or how many launches we need to build everything, to bring everything to orbit, to assemble a spaceship, then going to Phobos and orbiting around Phobos and around Mars, and doing exploration on Phobos and coming back. So designing a transit habitat or these elements at Phobos, it's part of the big picture architecture. So NASA defined 14 space technology grand challenges for Mars mission and space exploration. And the space architecture can provide design ideas for several of those challenges. It's space colonization, spaceway station as a gateway station, and moon and vicinity of the moon, efficient in-space transportation, high-mass planetary surface access, all-access mobility, and surviving extreme space environment. For all these challenges, it's really space architecture is important, and that's what we can bring and to the field, to the industry, to the space industry. Also, space architecture contributes to space exploration in many ways. So, and our motivation comes from the deep human drive to explore and inhabit new places. So also as an architectural discipline, space architecture organizes and interprets the creation and enrichment of built environments. We also strive for gaining new knowledge, as designing for space requires specialized knowledge of orbital mechanics, propulsion, weightlessness, hard vacuum, psychology of humans living in isolated and confined environment. And space architecture is multidisciplinary by nature and has complementary relationship with diverse fields such as aerospace engineering, terrestrial architecture, transportation design, medicine, human factors, space science, even law, and of course art is also part of it. So here is, this is a very generic table that shows why we would explore, as humanity, explore Moon, Mars, and going to orbit. It's important to understand why we're even going to space if we want to design for people. So why we're going and what is there for us as humans. So I usually show this in the beginning of the lecture and then ask the audience to think about other reasons, so more reasons. Why would you think that we need to explore space? Why do we need to go to space? Why we need to go somewhere where to places that we don't have enough knowledge even yet, what is there, what to expect. So please think about it, and maybe we can discuss it in the end of the lecture. So when thinking about space architecture and how it is related to terrestrial architecture and terrestrial architecture for extreme environments, we'll think about the challenges that we have to deal with when designing and building in extreme environments on Earth. And here is some comparison of, okay, so I think okay. Here is some comparison of and looking at the design process and general guidelines for habitat design in space. It's similar to design process, architectural process on Earth, but it has more challenges, and we need to deal with more input. Including that's much more challenging conditions and in space where we need to protect our clients, our humans who we design for, from very harsh environment. So as architecture on Earth, we design an envelope where we protect humans from harsh conditions or environmental conditions around them. In space, it's the same, but we also need to connect it with what mission objectives, space mission objectives. So what they will be doing there, how they will be doing, we call it the concept of operations on the surface or in space while going somewhere or in orbit. It's always a goal. There are always objectives what they need to do, and design really can help to accomplish it safely and to have a successful mission at the end. So when looking at design process, we look at, of course, examples and experience on extreme environments, in extreme environments on Earth. There are also many space analogs built on Earth under the water. And in harsh conditions, like in polar conditions, in Antarctica, also in Greenland, in deserts. Looking at all of that, the data that we can collect from those examples, analyze it, analyze and synthesize, and create a design that we can also think how we can validate it here on Earth. But of course, not everything, there are no ideal analogs on Earth that we can test all the design solutions. So eventually the final test will be there at the place, even in space, on Mars or Moon, when it will be built and humans will be living there. So a lot of loops when we go with test and retest our design decisions and applying it and testing where we can and what we can test here on Earth before this final design will be implemented and the final product will be flown and deployed. And again, when there's some correlations between conditions and considerations, design considerations in harsh environment on Earth and in space are related to ways how we can deliver our logistics and our elements to the destinations. So here is a comparison between launch rocket with a payload shroud here representing where we can put our elements, our habitat elements or structural elements that will have to be assembled either in orbit or some low Earth orbit or some other orbit or in Lagrange point, depends on the mission. And the ways how we can deliver structural elements here on Earth. So there are very strict restrictions, of course, for space. And but there are still a lot that we can learn from the ways how we Earth, and that the present on extreme conditions on Earth, including limitations on resources, availability of services and spaces, mobility and transportation is always limited, and all of that applies to space, but again, much more restrictive. So, grand challenges, and there are more, but in general, to summarize it, we would say that that of course space architecture differs from the terrestrial architecture in many significant ways, and mostly we have this great launch mass and volume constraints related to the payload shroud of a launch rocket, and we also have to deal with deep space flight hazards, radiative radiation, vacuum, extreme temperatures, microgravity, and on the surface of Moon and Mars, it would be dust conditions and weather conditions on Mars. So we have to protect the crew from all of that. We have to think how the crew will be conducting their EVAs, extravehicular activities, so how they will be getting in and out of the habitats, how we protect the crew when they are outside of the habitat from these harsh conditions, how decontamination will be happening when they come back to their habitats, and of course, dealing with human factors as the psychological, social, and cultural related issues, how the design can help for that is also part of the tasks of space architects when we design habitats for humans. And not only, again, the habitats that stand alone, but also in connection if we're talking about bases and settlements. So all those issues are also applicable to the whole settlement, and so how these elements will be connected on the surface, how they will be getting from one element to another is also important. So considering how we launch systems from the surface and how we come to the destination, it's selecting and thinking and understanding what kind of propulsion system can be used to go to, let's say, Mars or beyond Mars or farther destinations. That propulsion system is critical for making it happening. We want the crew to go and get to the destination as fast as possible, so they would spend less time in transit, exposed to radiation, so cosmic radiation and solar particles events, and to weightlessness, and that really depends on how fast they can get to the to Mars or to beyond Mars or other destinations in solar system if they go farther. So usually everything is assembled in low Earth orbit, and the crew arrives the last to get to the ship and take off. It's usually, I'm saying like how it's planned, usually how the mission is planned. So again, so far we haven't been anywhere farther than the moon, but for further other destinations, we need to think about it, how it will be assembled, how crew will arrive, and how long they will spend in space. So when designing anything and for everything, this power is the key. And considering that what kind of stable and reliable power can be provided for in-flight or at the destination on the surface of the moon or Mars or elsewhere. So stable and reliable power supply is the key for success of any space mission. Is it orbital or transfer or deep space flight? So selection of it to the mission power source defines not only spaceship or base design, but overall mission architecture and surface infrastructure development stages. And the effectiveness of solar power diminishes as we go farther from the sun, and also on the surface of Mars because of dust conditions and dust storms. It's also not stable or very reliable power source, especially if we're talking about settlements and providing support for bases on the surface of Mars, or any infrastructure that will require significant power needs. So also considering how that power source can be maintained, how it can be repaired and what can be repaired, how the power will be distributed on the surface, and also where it will be located in this in relation to the habitat or habitats if it's on the surface, how we protect habitats from it if it's a nuclear power source. So again, NASA designed, or NASA suggests that kilopower or megapower systems that are considered for Mars and Moon basis power supplies. And but for any type of power system, space architects have to consider their safe positioning and distribution infrastructure, how it will be connected. So connecting interfaces is important. How and often and how much it will require the maintenance operations, what are the backup systems, and what would be the emergency procedures if something happens on the surface. So as power is the key to survivability on the surface or during the flight, so that also requires a certain level of redundancy and a certain level of backup plans. So if something goes wrong, so at least the humans and on the surface in their bases, in their habitat, will survive till either it's repaired or new system is installed. It's also related to resupplying support missions, and designing of a space habitat base or the whole settlement requires understanding and integration of strategies for mission support and logistical resupply options. Type of a space mission defines what resupply options and strategies can be implemented. Design of those space structures should include the means, interfaces, and for receiving resupply ships, and provide adequate and optimized spaces for storage inside habitats. So if for orbital missions and for moon missions, we can rely on resupply missions from Earth on a quite regular basis. For Mars, that won't be the case, for example. So more storage will be required inside habitats, or additional logistical modules will be required to support the mission, surface mission for a long time. So how all of that is connected, what we can take with us, what we cannot, and how much we can rely on that stuff that we take with us is important. And it's also important the strategy, how you design the habitat and logistical support, for example, module attached to a habitat that the crew will eventually may use for different other purposes and functions as they use the supplies that they have in logistical modules, for example. So everything is also should be connected, and so connecting and designing the interfaces that provide multiple ways of connecting to multiple types of vehicles, and multiple types, different types of resupply ships and means. That's also important to consider. And again, now we are to habitability and talking about the crew. So designing means to help the crew to maintain their physical and psychological health is very important. Again, physiological deconditioning includes bone loss, muscle weakening, cardiovascular deconditioning, sensory motor disturbance, and vision deterioration. So, and many things that are related to microgravity conditions. And psychological issues are associated with living for a long time in isolated and confined environment, as are associated with sleep deprivations, and sometimes it creates depression and impaired cognition, and the crew may become irritated, and also that leads to their depression conditions and anxiety and hostility within the crew. So designing in a way that you can provide means for the crew to have enough privacy, but at the same time we don't separate them. We want the crew to be a cohesive team and effective team. So design really can help with that. And again, so the NASA astronauts in 2019, they put together a memo for the JSC Johnson Space Center flight director, where they're talking about important things that they consider for long duration space flight. And it's a quite long list, but several things are very interesting and very much related to space architecture, because they said that they need to make sure that they have crew quarters that they can be accessible. They can be accessible 24 hours at any time of the day. So it means it cannot be something that they really only use during the sleeping. They need to have their privacy, or a means, a way how they can go and have their privacy at any point during the day. Also, having a window is important. And on one hand, you would think that flying to Mars, you don't see much when the Earth is already far away and Mars is still far away. But having a window is still important to having the relationship, and being able to look outside is still important. So there are several essential issues that astronauts consider that will be critical to have in the habitat during especially long duration space flight. So the purpose of architecture has always been to serve people and their needs, and providing a safe, convenient, and comfortable environment for living and working. And so architectural means, methods and means and meanings, how to achieve those goals has been changed. And social, political, and geophysical, and technological changes influence human life and reflect onto architecture and design practices on Earth and outside Earth's boundaries as well. So it's all applied also in space architecture. So, of course, thinking about ergonomic, functional, human factors and perceptual aspects of design in space becomes very critical for designing for long duration space flight, and also for settlements and base on the Moon or Mars or elsewhere. So designing, again, of course, we have to design with this confined environments. So how some spaces can be multifunctional and serve different purposes during the flight on the surface at different time of the day. The same place can be used for different functions, but as I said, certain functions require more privacy and also require certain conditions. For example, hygiene will be always where it is. It requires connections to water supplies and recycling systems. So it will be always there, but other places can be rearranged depending on crew needs. But also designing for different gravity conditions and gravity levels, they influence on design for space facilities very, very much. So here is some considerations, design considerations, and how they can be dealt with, and what are the conditions and considerations, design considerations in different gravity conditions. So here's microgravity. It's of course in low Earth orbit or in flight somewhere to Mars or Moon. For partial gravity, we're talking about Moon or Mars. And artificial gravity is an alternative solution for long duration space flight if we want to provide it as means to provide health support for the crew during the long space flight as a mitigation for microgravity conditions, for zero gravity conditions. Again, regardless of material used and regardless of gravity conditions, all elements designed for space are pressure vessels. And that means they are either spherical or cylindrical or toroidal. So this all depends, the geometry depends on the pressure distribution, inner pressure, atmospheric pressure distribution. And we want this pressure distributed evenly. And to support the structural integrity. So that's why most of all of these pressurized structures are in these shapes. So far, most of the structures that we have in space are hard shell modules that I will talk in the next slide. And so they were used in space stations, starting with Salute and Skylab and Mir, and now in the ISS. They're all hard shell structures, and they have certain advantages because we can install all the equipment or most of the equipment on Earth and launch this element as is, test it first and then launch it to orbit, and it's already, everything is in place and ready to be used. There are disadvantages, of course, because the size of this module depends on the launch vehicle payload shroud dimensions. And the ISS is built with using shuttle, and dimensions of the modules were according to the shuttle bay. So that helps to build the ISS as it is right now. But other launch vehicles, they have a smaller payload shrouds. Well, now they are bigger ones, and heavy lift vehicles are proposed and designed, and now it's under testing. So that will give us an opportunity to have a larger diameter of these modules, yet it's still limited to the payload shroud dimensions. And we always want to provide, especially for long duration spaceflight, more volume, more space for the crew, and for systems and for the stowage. So that is always the consideration, how we can expand those modules, how it's possible to launch it small and then expand it in space. So here is one of the options, having a telescopic hard shell modules. So a lot of that, some equipment can be pre-integrated and installed in this inner portion of the telescopic module, and then once it's in place, can be expanded as is. So it provides, it doubles, almost doubles interior volume and real estate, so area that can be used. But it also, those type of modules will be quite heavy to launch, and also there is a potential for leakage where these two parts of the modules are connected. And for the surface, that will definitely be a challenge, because you have to provide and think how this expandable portion of it will be supported on the surface. Partial gravity is still gravity, so you still need to support it. Other deployable structures are inflatable, so the most popularized expandable structures are inflatable ones, of course. And they offer more volume with their diameter increasing, and they also can be packed inside the payload shroud during the launch. Some significant disadvantage, though, of those modules is that everything has to be packed somewhere else during the launch, and then once it's expanded or inflated at the location, so only then the module can be outfitted. Interior outfitting can be deployed as well. So that will require more crew time, and it also will require certain conditions and means how it can be all connected inside and installed inside an inflatable structure. Also include installing interfaces in inflatable shell. Of course, it's challenging because it's also potential for leakage and all of that stuff. Also, of course, this inflatable wall is not just a thin wall, it's a multi-layered structure, which is also quite, has to be quite durable and protect the crew from these micrometeoroids, and potentially we want to include some radiation protection layers if possible. So that all of that also requires special considerations. So here's some more examples of what can be installed there. So here's an example where toroidal inflatable structure is used for a greenhouse, or to put plants around there. So the plants will be in a rotating environment and rotating chalices inside those toroidal structure. So overall, so for microgravity design considerations, what again space architect needs to think about as again mitigation for physical health hazards associated with microgravity conditions. It means exercising and exercising equipment. Need to provide visual cues for the crew where to go, as there are no ups and downs, so where they go and how the modules are located, and where they're located and how they oriented. It's important for the crew to know. Then zoning is important, and it's what is very important is also to think about life support systems and how the air circulation is happening inside those modules. We don't want to create deadly pockets of dead gases in this microgravity environment. We also need to think how the water and all the fluids will be distributed, where the pumps are, and where all these utility runs will be placed and organized. So how to help the crew to secure themselves in positions, how all these elements will be secured in the position where they need it. In microgravity conditions is all important things to consider. To think about the ways to mitigate the physiological deconditioning associated with the microgravity environment. So artificial gravity sometimes is proposed, and artificial gravity is provided by rotating a habitat or the whole vehicle, and making this rotating environment as a countermeasure or a substitute for gravitational forces. So it's very difficult to design such vehicle because it requires quite large diameter to make it more comfortable for the crew. So it's a big engineering task how it can be designed. Still, it's interesting to consider, and it's interesting to think in what way artificial gravity can be introduced and as a part of the spacecraft, and that doesn't maybe using a centrifuge or just one element where this the crew can be spending some time during the flight, and it will help to mitigate some negative effects of microgravity conditions. So there are many different designs looking at it. So here is example of artificial gravity science and excursion vehicle proposed by our center a long time ago. It was also supported by Bigelow Aerospace, and designing as a hotel going to the moon, rendezvous around the moon and going back to Earth. It was quite interesting story how all this project happened. I can tell the story later if we have time. But this is one example how it can be done. Of course, again, in rotating environment, there are some also issues. And one of the issues, people may experience motion sickness. If you go one direction, you change to another direction, your inner ear will be confused and may create some deconditioning also, but maybe people can adapt to it fast, maybe not, we don't know yet. So it's another example of also rotating environment where there's all the habitats were located on one side, and the storage was on the other as counterweight to create stability of the structure when it starts rotating. As I said before, committing and building such large systems, perhaps we can test smaller versions of it and see how it will affect rotating environments, would affect systems and humans. And here's another proposal from one of our students to use pre-child module and progress as a tag vehicle, and two Dragons capsules connected to pre-child, and then they would first they dock to the ISS and then undock and start rotating, and then we can test how systems, how fluid dynamics work in a rotating environment, what needs to be adjusted and what needs to be redesigned there, and then maybe humans can also spend some time, and we will see how fast we adapt to rotating environment in micro G conditions or in orbit. So that's before we're building something like that, so it's a larger scale, to test it in larger scale and to get ready for developing something in partial gravity conditions. Again, we don't know how fluid dynamics or how humans will react to partial gravity conditions. So that was the proposal, to build a rotating environment in orbit where in the middle it will be 0G or microgravity conditions. Then in the middle it will be simulating 1/6 of gravity like on the moon. And at the end it will simulate 1/3 of gravity like it was, is on Mars. So before committing, going and building something big there, so we can test systems here in orbit in rotating environment. Again, going to the surface of Moon and Mars, and of course talking about Mars. So we need to think about many issues. So first of all, of course, where the bases will be located, how we land there, what we land there, and how we will land, and how, again, there are no roads, and there is no infrastructure, especially at least in the beginning of these developments. So site conditions and location and landing and transportation means is very critical. And we do need to think about it when we design these elements. So what we can provide, how steady is this, and how balanced the structure will be when it will be landed, and how it can be safely delivered from the landing site. And again, what is in situ resource utilization? It's what ISRU stands for. What is available at the site, what they will be doing, and how we can start testing things there. So here is an example of, probably you're familiar with these results of NASA's 3D printed habitat, Mars Habitat Challenge that was launched a few years ago. And this proposal is from CARCH, and that they won their BEAM stage, so it's the design stage of this challenge. They didn't build a prototype to test, but they won the design part of it. And so still, these kind of structures will require a lot of infrastructure already installed and a lot of power already in place. So that's definitely something that won't happen at once. Again, to print something like that will take many, many years. So perhaps what we will start with just delivering, again, hard shell modules first, and then think how it can be expanded further. Again, on the surface, still conditions are present that we need to protect the crew and its radiation, micrometeoroids, extreme temperatures, and Moon and Mars, still the same things we need to consider. So radiation is a big issue, and how we protect the crew and important assets inside the habitat is critical. Either using regolith on top of the structure, but then need to think how much regolith it will require, quite a lot. Doesn't matter what type of modules we use, so probably we'll have to use retaining walls to minimize the amount of regolith to be put there. Or for solar particles events, we can suggest having deployable structures inside the habitats using water as the best radiation protection matter. Or using, again, local conditions and local topography to our advantage, including sides or slopes of the craters on the Moon, or using ridges, dust ridges also of the Moon or Mars, and see how we can put our habitats inside or inside of this, using these features to benefit from them. Still will require quite a lot of work, and that is also something that the space architect needs to consider, how you will do it, what will be happening, what are the stages of the development. Again, another, of course, looking at lava tubes. Lava tubes is interesting. On one hand, it's an interesting location, and it seems like it's already there, we can use. On the other hand, we have no idea what is inside. So hopefully these future missions and those to investigate those lava tubes, that's currently under development, right? So it should be, we should know more soon, and then can design accordingly. Still, considering how you get there, how those modules will be connected, how you put them in, how you will communicate with these habitats under the surface, where the airlocks will be located, how if something happens, how you can replace those modules. But those are all things that space architect needs to think about. The whole thing, it's not just one element, thinking about from the very beginning and from the very end of life of the structure, how it's all connected, what's required, what needs to be done. Okay, so here is coming to the questions. I have a short video, but I think sound doesn't work for this video. But perhaps we can go with the questions first, and then if we have time, I can show the video. Okay? Thanks.
Hey, Olga, thank you very much. If you have any questions, you're welcome to put them.